Okay, so this mini lecture is about free fall. And what is free fall? What are some examples of free fall? And what's some information that we can understand and know just by knowing an object is in a state of free fall? So, what is free fall? Free fall is defined as an object under the influence of gravity only. So, nothing else is affecting its motion other than gravity. So it's falling freely in the air. Now, typically we think of falling as actually heading towards the ground. But in this case, falling freely in the air just means it's just in the air, and gravity is the only thing affecting its motion. So if an object is dropped and falls to the ground while it's falling to the ground, it's in free fall. If an object is thrown down and falls to the ground while it's falling to the ground, it's in free fall. If an object is tossed up, as soon as it leaves my hand, I'm not influencing it anymore. The only thing affecting its motion is gravity, and it is also in free fall. It's in free fall on the way up, it's in free fall on the way down, it's in free fall the entire time it is out of my hands. And as we'll find, even if I chuck it across the room, it's also in free fall. We're only going to worry about one dimension, so just the up and down until we get to that projectile motion, but we'll see that too is a state of free fall. So let's look at those three cases: dropped, thrown down, and thrown up. And let's see what other things might be implied just by knowing that's how an object is in existence, is behaving in its motion. So we'll start with an object being dropped. So we are interested in various players of motion, right? Various positions and various velocities and various accelerations and times. When an object is dropped, it tends to start at some position. Now, we can define that position to be 0. We can define it to be whatever we want it to be. But we do know that when it is dropped, the final position will be lower than the initial position, physically in space. The final position will physically be lower in space than the initial position. That's one thing we know about a dropped object. We also know that the initial velocity of the object is equal to 0. As I drop an object at 0, right before I let go of it, when I let go of it, as gravity is starting to take hold of it, it starts at 0 velocity. So a dropped object has initial velocity of 0. It will have a final velocity that is non-zero. And more importantly, and also importantly, that if I drop it, it will always be moving down. So its final velocity, whatever point in time later I'm interested in, will have a negative non-zero value. Now, what about its acceleration? How will that look? Well, it is changing its velocity, so we know its acceleration is going to be non-zero. What about its direction? As I go from a 0 to a non-zero value, I am speeding up. I'm getting faster and faster and faster. I'm moving down. So if I'm speeding up, my velocity and my acceleration have to be in the same direction. If I'm moving down, my acceleration has to be down. So for a dropped object, I know my final position will always be lower than my initial position. It will end up below where it started. I'm going to always have a velocity equal to 0. So even if I am not told that in the problem, if I am told or I am analyzing somebody dropping something, my initial velocity is 0. And again, this isn't just this vertical dimension. My final velocity is going to not be non-zero because it's going to start speeding up, but it's going to be moving down, so it'll have a negative non-zero value. If I'm speeding up, my velocity and my acceleration have to be in the same direction. My acceleration is also negative. So those are some things that we know just by knowing an object is dropped. What if an object is thrown down? So I don't just let go of it, I chuck it. Once it's in free fall, once it leaves my hand, that is what we're interested in. So my final position is always going to be lower than my initial position. If I throw something down, I'm starting at some position. And I'm going to end up, when I let go of it, that's when it hits free fall. This part, not involved in the free fall. That's a totally different acceleration. The phase that's free fall is once my hand lets go, and it is only under the influence of gravity. So my final position will be lower than my initial position. My initial velocity, well, I'm not just letting go of it, it's actually moving when I let go of it. So my initial velocity will in fact be non-zero. It's already moving when I let go of it, but it is moving down, so it is a negative non-zero. So when I throw something down, my initial velocity will have a value that is non-zero and negative. My final velocity, well, it will also be negative non-zero. It started moving down and it's going to keep moving down. So it'll stay a negative non-zero. It's not going to be the same negative non-zero, but it will be also a negative non-zero value. What about acceleration? Well, as I throw the object down, it starts off with a non-zero negative value, but then it gets faster and faster and faster. So if it's speeding up, acceleration and velocity have to be in the same direction. So acceleration will also be negative non-zero. Speeding up, moving down, same direction, negative. So that's an object thrown down. After it leaves your hand is when it becomes in free fall. We're only looking at assumptions and implications we can make with free fall. What if I throw an object up? Well, it's easier to analyze an object being thrown up if we think about it on the way up and on the way down separately first, and then look at how that's related. So let's look at the way up separate from the way down. And then we have this little at the top transition from the way up to the way down. So on the way up, x final on the way up is going to be higher than x initial. It's heading upward. So if I just get to that peak on my way up, then the final ends up above wherever I started. It's moving when I let go of it, or it wouldn't keep going up. So my initial velocity for the way up is non-zero, and it's moving upward. So it has a positive non-zero value. So it's moving up, it's moving, non-zero, and it's moving up, positive. What about my final velocity? My velocity at the very, very top. What does the object do right at the very, very top? Well, it slows down, slows down, slows down, slows down, passes through zero, comes to a zero velocity very, very briefly before it turns back around. So at the very, very top, I have a zero velocity. Now, we knew it was slowing down, because it made that turnaround transition. So what is my acceleration? Well, it's changing velocity, so this has to be non-zero. It's slowing down. If it's slowing down, that means the acceleration and the velocity are in the same opposite. They're opposite directions. So if the velocity is positive, the acceleration has to be negative. So this negative acceleration is a slowing down because my velocity is positive. What about on the way down? Well, at that transition point on the way down, my final position is going to be lower than my initial position. As it's going down, I'm going to end up below where I started. My initial velocity on the way down, well, it gets up to the top and turns around at that 0 meters per second. So on the way down, my initial velocity is 0. My final velocity, well, it's going to be speeding up as it goes down, but it's going down, so it'll have a negative non-zero value. As it's speeding up, if it's speeding up, the acceleration and the velocity have to be in the same direction. If the velocity is negative, the acceleration has to be negative. So I have a negative non-zero velocity in that phase as well. What about at this very, 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 very top? Well, position's sort of irrelevant. It's just what the position is at the top. My velocity at the very, very top passes through that zero. Right before it hits zero, and then immediately after it hits the top, it's changing. It's getting to zero, passing through zero, and then getting away from zero. So at the top, we want to think about it as passing through zero. It doesn't stay there. It keeps changing. And if it keeps changing, there has to be an acceleration at the top because it's changing. And what does that acceleration look like? Well, if it was negative slowing the object down and negative to speed the object up, it too is negative at the top. So we notice that acceleration in every case of free fall is a negative non-zero value. And because it's only gravity influencing it, gravity, as a result of the mass of the Earth, doesn't change from state to state to state, from situation to situation to situation. It's the same Earth affecting the same objects. And so value is a constant. And our acceleration due to gravity is equal to that negative, so our direction is in here, 9.8 meters per second squared. And that is a constant that we will use over and over again. So when it's dropped, the acceleration is negative 9.8. When it is thrown down, the acceleration is negative 9.8. And in every phase of being thrown up, during the whole motion of an object going up and then down, the acceleration is negative 9.8. Every object experiences the same acceleration due to gravity. When we describe an object's motion, and we've been describing an object's motion, the type of object isn't even a part of the consideration. We don't consider its mass. We don't consider its shape. We don't consider its size. Every object is just considered as a single entity, a single mass, a single thing, and the motion is described based on other variables, the positions and the velocities and the acceleration. The same is true in free fall until we get to a point where air resistance comes into play. And we are no longer in free fall because there's another influence, air. All objects will experience that same acceleration due to gravity, regardless of their shape, size, and mass. So the acceleration due to gravity is constant. It is constant in magnitude, 9.8, and it is constant in direction, negative, for following convention. It's always pointing down. All right. Don't forget that. Don't forget some of these things that we can imply about motion that we know exist because of an object being dropped or an object being thrown up or thrown down. Use those ideas to solve problems in free fall. Good luck.